Hi everyone, my name is Matt Wills. I'm Market Director for Low Carbon and Onshore Projects for Kent. I've been with the business for 15 years and I started on low carbon work over a decade ago. I've led Kent teams on waste to intermediates plant designs, on CCS and on hydrogen projects in order to reduce the carbon footprint of the chemical industry. So why consider chemicals? Why this topic for our tech talk today? Well, our civilization is predicated on chemistry. Just look at the room around you. See the chemicals that make our way of life possible. Paint on the wall, varnish on the desk, your laptop monitor cases, your keyboard, your mouse, synthetic textiles in clothing, cosmetics, PVC window frames. The challenge with decarbonisation is most of the quantity of the chemicals we use are produced from fossil feedstocks. The chemical sector is the largest industrial consumer of both oil and gas, resulting in greenhouse gas emissions in production and then downstream either at the point of use or the end of life. And the scale is huge. 2019 data, ethylene, we use 190 million tonnes per annum. Propylene, 120 million tonnes, aromatics, 70 million tonnes. And that carbon is fed into society and when finished, maybe burnt or landfilled, potentially adding over another gigaton of CO2 or equivalents per annum of greenhouse gas emissions. So the challenge is, how do we tackle decarbonisation of chemicals without ending our current way of life? At Kent, we are experienced in decarbonisation through electrons. So, for example, our offshore wind team, run by my colleague Kerry-Ann Cummings, or, for instance, power with carbon capture and storage. We've looked at the decarbonisation of transportation. For example, one of the waste to sustainable transport fuel projects that we've worked upon. And we've looked at the decarbonisation of domestic and industrial heat. For example, the HyNet low carbon hydrogen plant or green hydrogen designs led by myself. These areas have received substantial attention from governments around the world and are being actively decarbonised. However, we've seen much less attention given to the decarbonisation of chemicals. We have ourselves produced designs for a number of CCS schemes and waste feedstocks to chemical precursors. Our first objective today was to raise with yourselves the scale and the importance of the decarbonisation of chemical production, to raise this as more of an issue for all of us to address, and to explain further the potential CO2 footprint of the industry. And then I'll hand over to my colleague Luigi, who will talk through the potential routes to decarbonise the chemicals industry, and then look at some of the long-term options, so alternative approaches for chemical production or alternative feedstocks to fossil fuels. So in terms of CO2 emissions, although I've just said the chemical sector is the largest industrial consumer of both oil and gas, its footprint is only 6% of global greenhouse gas emissions. And that's because a lot of the carbon that's going into chemical production comes out the other end as the products. And we only then see the CO2 emissions at the end of the life of those products or at their point of use. However, 6% is still a substantive part of the overall greenhouse gas emissions of our civilization. The concern around chemicals is that over time, we're seeing that chemical demand is growing significantly. So we're likely to see chemical demand grow 4 times over 4 decades. And as I've talked about earlier, we've seen that other routes, decarbonisation of electrons, transportation, heat, is well addressed. Chemicals is not an area where we've seen a lot of progress. And therefore, with other sectors running down and the greenhouse gas footprint of chemicals increasing, This is likely to take more and more a part of the global greenhouse gas problem. So what I want to do now is hand over to Luigi, and Luigi will take you through routes to decarbonising the chemical industry and potential alternatives to fossil feedstocks. Thank you.
Thanks, Matt, for the previous slides. I'll just give a quick introduction to myself before I continue with the slides. So my name's Luigi. I work in the low carbon team here in Kent, with my focus mostly on technologies. So looking at gas reforming, CCS, green hydrogen production facilities, and a variety of synfuels as well. So a whole spectrum of technologies that would enable us to develop low carbon fuels. So the next few slides, as Matt was saying, is a need to decarbonise chemicals. So I'm going to talk you through some of the maybe processes that we can use today and in the future to develop. So the first chemical I looked at was methanol. So how do we decarbonise methanol? By using biomass. So currently methanol is produced by natural gas or coal. Natural gas and coal basically produces hydrogen, CO and CO2, so a syngas mixture. Coal typically uses steam treatment in excess of 1000 degrees. Natural gas is usually a reformer, a little bit lower in temperature, 800 degrees. And coal tends to have some more pre-treatment work to be done due to some contaminants and impurities that they may have. But basically what we're trying to do is develop the right ratio of hydrogen, CO and CO2. And this can be done also with a water gas shift reactor, which is noted there. Any excess CO2 does get vented to the atmosphere. And the synthesis itself, so the methanol, is done by catalytic process, usually based on a copper or zinc oxide. And then finally, there's a distillation of the crude methanol produced, just to remove some of the water that's produced within the process itself. These typical methanol processes range from about 2.5 tons a day to 5 tons a day. So reasonably large capacity, and production costs ranging around about the $200 US dollar mark per ton. So what can we do to improve or decarbonise this traditional methanol process? So there's a new pathway of using biomass as a feedstock. So biomass, shown there in green, can include things like forestry waste, agricultural waste, sewage, waste wood, municipal solid waste, obviously depending on the source, because what we're trying to do is develop the biogenic content or the biogenic carbon, makes the process biomethanol. So the feedstock itself, because we're using a feedstock which is typically solid, more solid rather than gaseous, there are different types of preparation to be done beforehand. So the solids have to be churned into small particles. There would have to be a screw mechanism or a plunger type. And this feedstock is put into a gasifier. So gasification is similar to a coal gasification system. But this one here was typically driven by oxygen, because we don't want any nitrogen within the actual process itself. As a rule of thumb, 1 mole of nitrogen in the upstream feedstock represents 4% nitrogen mole percent downstream. So we're trying to, so we always use oxygen. Generally, for gasification, there's two types. There's a slagging and non-slagging type. Non-slagging around about 800, 900 degrees. Slagging is about 1000 degrees. So due to the lower temperatures non-slagging, we usually have a second unit, maybe such as a POX or a plasma reactor. This is just basically to remove any tars or methane that might have slipped through the non-slagging gasification part. The gasifiers themselves are usually put into parallel units. This helps with operability and for ton down, for example. But at the end, we're always trying to develop the right ratio to produce syngas to methanol. So once the right ratio is produced, the methanol synthesis is pretty much the exact same as what it is for natural gas and coal. So chemically, the biomethanol and the fossil-based methanol are the same. Interesting here, and then also moving on to some issues. So as with all new technologies, there would be some issues around that could bring the costs up. So things like such as seasonality. So biomass is quite seasonal, or can be. So for example, in winter time, during festive periods such as Christmas, you might find there's more phosphorus within the biomass itself. Biomass may be from household waste. And this is because we might have more chicken bones, for example. And the feedstock itself, there'll be a drive between producing either a crop biomass for food for humans, or crop to produce biomass for a chemical production of biomethanol. So there'll be some give and take there. And in these policies, as with any fuel, we need to have stimulate the supply and demand for it. So this is where government should really step in to help the policies, regulations, and mandates to try and push through biomethanol. I thought to give you some indicative figures there. So currently we produce about 100 million tons per year of methanol. So to produce that volume of methanol, that mass of methanol, we need approximately 340 plants of 500,000 tons per year. Just give a size of scale, 500,000 tons per year, that's equivalent of a city of size of Edinburgh. I'm from Scotland, so I know Edinburgh, the size of it. So you need approximately 340 equivalent size Edinburgh cities dotted around the world. So it's quite an undertaking to do. It's quite a large process capacity that needs to be done. But biomethanol is possible. Another application we can use to drive down the decarbonisation of methanol is the use of hydrogen. So again, I've shown here the coal, natural gas coming from the left-hand side, same processes all the way through to produce fossil-based methanol. But this time, what we could do is we can use electrolysis of water to produce green hydrogen. So this is producing e-methanol. So e-methanol is considered as a new e-fuel, so power to X technology. So once we produce this green methanol, this green hydrogen, we also need CO2. So the CO2 can come from air. It can come from biomass. So distilleries usually have biogas, so a form of CO2. But we'll also get the CO2 from fuel gas, from power plants. So obviously the CO2 would be fossil based, but instead of just venting it to the atmosphere, we can at least use it one more time to produce a product such as methanol. So, but it wouldn't be classified as green fuel. So as before, there's also a pre-treatment of water. So we're looking at bringing the water quality or removing the minor components of the water itself. So we're looking at using applications such as reverse osmosis, and we're looking to values such as conductivity, chloride, silica. And another new area of interest is actually producing hybrid plants of biomethanol and e-methanol. So basically we have the advantage of you having consistent biomethanol being produced through the process. And then we also have the e-methanol combination. So one new area of interest is the hybrid plants. This combines both the biomethanol process and the e-methanol process. So the advantage of this is that in the e-methanol process, where we produce green hydrogen, we also produce oxygen. That oxygen could be used to fuel the gasification reaction for biomethanol. And also it gives us the advantage that green hydrogen can be quite fluctuating because it's based on wind or solar energy, a renewable source of energy, which can be quite fluctuating itself. So we can have a mix and match of biomethanol and e-methanol to maintain the product output. So as I said before, there's drivers to bring down costs. These are new technologies. So one of the things, as I mentioned there, was the source of CO2. So currently air, as noted there, it's 0.04% more volume of CO2 is in the air. So we need a large volume of air to be processed to capture some CO2 for the process itself. And you can see here it's quite expensive at the moment. So direct air capture, DAC, 600 tons per CO2 captured. We also have electrical source, I just mentioned there, the fluctuation of that electrical source. So we may have to have the requirement to have grid connection to these processes. So we have periods of where we actually produce green hydrogen and then periods of not. And the scale, just to give an idea of the scale of these things. So I've given you a small table there. So 100 million tons per year of methanol. What does that look like if we have to do e-methanol? So we're looking at about 100 to 110 number of plants at sort of the 100 gigawatt scale. Just give it an idea of today's scale. Like green hydrogen, electrolysis of water, you're looking at maybe 100 megawatt scale. So this is 100 gigawatt scale. So you can see the amount of increase in production of green electricity we have to produce. Next slide, I looked at ammonia. Again, ammonia is a precursor to many chemicals that we use in everyday lives. So typically it is produced from natural gas and coal. That's about 70-30 split. Typically it uses about 60 gigajoules per ton of ammonia of energy. That's quite energy intensive. And there's about 500 plants of ammonia plants around the world. And we produce around about 200 million tons a year. And each plant has about a range of about 200 to 1,200 tons per ton per year. And the amount of CO2 produced in 2020 due to ammonia was 450 million tons. So definitely an area we could try and address. So the current status of this shown there, we have basically the main steps of isolating a hydrogen atom, a hydrogen molecule, from natural gas, isolating nitrogen from air, typically done by an air separation unit, and then combining the hydrogen and nitrogen together. This is done with a Haber-Bosch process. Haber-Bosch process, high temperatures, 400 to 600 degrees, high pressures, 200 to 400 bar pressure. So as I said before, very energy intensive. About 60% of the process energy is developed from actually the feedstock itself, is used up from the feedstock. So what can we do? Well, there's new ways of bringing down that CO2 emissions. So we can do that via CO2 capture units. So these can typically range between 85-90%, but they can go as high as 99%. This can be done by using new technologies such as chemical absorption, using amines, or there's new advances in amine solvents as of today. And then also as a side note, we can also use actual green hydrogen. As mentioned before, green hydrogen produced from renewable energy, which is fluctuating. So what we've seen recently is retrofits or new additions to plants with a small injection of green hydrogen developed on site to displace some of the grey or the brown hydrogen produced within these processes. But basically addition of that carbon capture unit produces blue ammonia, and therefore drives down CO2 emissions. The CO2 is actually sequestered. So some of that, as before, there's some areas to bring down these costs. Yeah, so basically location is quite important. You know, when we actually have these CO2 emissions, we would like to have these plants close to an area where there's a CO2 sink. Industry would have to look at itself as well. I've talked about retrofitting some of these areas. So industry has to get involved and see where we can actually retrofit these carbon capture units. And again, policies from governments to drive down the long-term CO2 emissions. And I've mentioned there a few values there. So currently we produce, as I said, 450 million tons per year. That's about 200 million tons a year of ammonia. So I hope that gave you a sort of flavour of some of the processes and some of the chemicals that they can be used on. There are many areas that we can spend hours, days talking about. So just these are some of the highlight ones. So big things that we've talked about is electrification of heat, maybe. You know? One of the things, areas that is usually feedstocks or natural gas are used to produce high temperatures, so 1,000 degrees plus. Electrification doesn't really lend itself to that. So how do we get around this? We talked about use of hydrogen, the use of biomass, so driving down the non-biogenic content of feedstock to biogenic content of feedstock. We've talked about the carbon capture and how we can sink it, and also with plastic recycling. So plastic recycling, I've not touched that, it's another topic all by itself, but basically at the moment it's usually done by mechanical recycling rather than chemical. So chemical will usually need more energy, so that brings on to the electrification of heat. And there is actually some new development work coming up where actually we can convert CO2 by electroreduction. So basically using an electrical impulse to break down the CO2 into feedstocks or products such as formic acid, CO or methane. So it's quite a new area, but all these can be a precursor to plastics. Again, so developing that area of how do you recycle plastics. then on the right here, you can see some of the challenges that face implementing these processes. So typically, assets are long-lived, 30, 40 years. So changing them to new processes, new greener, blue processes, can be quite expensive because the plant's already been built in to have that cost enveloped. There's high temperature and high heat requirements. So we've mentioned that before. So we're looking at reactors running at plus 1,000 degrees, and that's typically done by a fuel such as natural gas. So developing a process that can bring those temperatures down, or using electricity would be advantageous. And then there's the process emissions as well. So there are several key industries such as the cement industry that naturally just produce CO2, and that could be when they actually produce like clinker to produce cement. So perhaps we can start looking at alternative binding agents rather than using clinker that naturally produces CO2. And then there's trade considerations. Many industries products are traded globally in a highly competitive market. So this could not only just chemicals but also steel, aluminium. So it makes it very challenging for a producer or a country to run with to invest in more expensive low carbon technologies to reduce emissions without being undercut by price by others. So where does it take us? Well, as a summary, chemical productions and industry account for about 1,000 million tonnes per year of CO2. Definitely an area we have to address. But there are many new approaches. I've given you hopefully a brief flavour of some of them in the presentation before, whether it be CCS, blue ammonia, or e-methanol. And there's a long road ahead, but even though the costs are high, I think morally it would be the right thing to do.